the last part, last type of converter, which is the so-called full bridge converter. So that is mostly used for motor drives. And is for motor drives and for DC to AC conversion in UPS. This is useful because it's one of the most common types of converter used for application to actuators, is used in very general cases, and it's interesting to evaluate. Let's assume that we have a constant voltage provided, for example, by a battery, and we want to provide energy to a motor that can be a fan, for example, or another type of actuator. Now, the full bridge configuration is consisting of the following thing. We have two nodes, which are A and B, and each node is connected to the higher voltage and to the lower voltage with a switch. We can call it TA plus and TA minus. And of course, these two switches can be alternatively on and off. If TA plus is on, then A is connected to plus V in, and therefore TA minus is off. And we have a second point B, which is again can be connected to the high rail TB plus by a switch TB plus and by a switch TB minus to the lower rail. Okay, these switches are typically realized as all the other switches with N MOSFETs. They are N-type MOSFETs, which can be, of course, in linear mode, in which they behave as a closed switch, or in cutoff, in which they behave as an off switch. Now, these 2 points, A and B, are connected to the motor drive. So here we have a motor, a DC motor, which requires a DC power supply. Okay? So typically, if the point to consider is that in a DC motor, DC motor is typically used for a fan to dissipate the heat in a computer, for example, or to an actuator. They typically are DC motors. And the important thing to consider is that from the electrical point of view, this supply voltage goes at the terminals of an inductor with of an inductor. So typically it has a from the electrical point of view, you have something like a resistance in series to an inductor. Okay. So this is important because the behavior is very similar to that of an inductor. So it tries to maintain the current through the motor. So the output voltage here is like this. The average output voltage is the average VA minus the average VB. The way in which this works is quite simple, in the sense that depending on the duty cycle of TA and TA minus, I can have a rectangular wave on the node A, which can have an average value between plus V in and 0. And again, I can obtain the same for B. So basically, depending on the duty cycle, VA can go from V in to 0, and VB can go from V in to 0, and therefore VO can go from plus V in to minus V in. So I can vary the average value of the output voltage between plus V in and minus V in, which means I can have both positive and negative values. When I apply a positive value to a DC motor, this no, let me not do this consideration. Only this. Yeah. Let me now make some calculation. So, let's consider VA as a function of time. When TA plus is on, VA is equal to V in. When TA minus is on, VA is equal to 0. So VA is something like this. For example, let's assume that this is the period. What we have is that in this time I have TA plus on and TA minus off, and during this time I have TA minus on and TA plus off, and during this time I have TA plus TA minus on and TA plus off. Okay, so depending on how I control these two switches, I can have a rectangular wave more or less with the shape that I want, and the average value of VA is equal to the duty cycle of TA plus, that I can call DA, times V in. DA is the duty cycle, so which is the fraction of the time during which the TA plus is on. Duty cycle of the TA plus. Of course, I can repeat the same type of reasoning for VB, for B. Therefore, also this is going to be the duty cycle of TB plus times V in. Okay. And therefore, the average voltage applied to the output is going to be the duty cycle of TA plus minus the duty cycle of TB plus times V in. And of course, it can vary from plus V in to minus V in. So I can really, depending on the duty cycle of these two switches, vary continuously the average voltage applied to the output. And this is something that it's very, very convenient, because, for example, with the positive VO, I can accelerate the motor. With the negative BO, I can put brakes on the motor, basically, just by applying a negative voltage. So, how do we apply these two duty cycles? Yeah. For example, let me show you just a couple of examples. One example that we can use, and it's very common, is the so-called PWM with bipolar voltage switching. And in principle, it works like this. Let me show the principle, and then we can discuss a bit how we do it. Basically, we have a sort of triangular wave, like this, periodic triangular wave. That we call V3, for example, and then a control voltage, which is this one, that we call V control. So V control can vary, and V triangular is fixed. And then we do the following thing. When, let's put it, if V control is larger than V3, then TA plus and TB minus are on, and of course TA minus and TB plus are off. Okay. Let's do it in the following way. Of course, if the opposite is true, the opposite is true also for the switches. Okay, so I write only one condition. If it goes in the other direction, then if this is smaller, then the first two are off and the last two are on. Okay, and then we can, therefore, once we know this, we can compute the, we can draw the voltage VA and VB, because of course when V control is larger than V3 is in this region and in this region. And for VA, when TPA plus is on, VA is equal to V in. So this is VA is equal to V in. When this is not true, VA is equal to 0. And then here is equal to V in. And then is equal to 0, and so on. Okay? And of course, this is a period. No, the period is, no, sorry, this is a period, right? From here. When you arrive at the same conditions. Okay? So, VB is completely the opposite, in the sense that when V control is larger than V3, TB minus is on, so VB is 0, otherwise VB is equal to V in. So we have an opposite situation here. Okay. So we can now plot the difference. VA minus VB, and if we plot VA minus VB, the situation is pretty easy to understand, because here the difference is equal to V in, and here the difference is equal to minus V in. V in minus V in plus V in minus V in, and so on. Now, okay, we have done. You see that actually the output voltage is a rectangular wave that, of course, has an average value, which is probably this one. So we are not exactly supplying a constant DC voltage at the output, even if this is a DC-DC converter. We are supplying actually a rectangular wave function that has a constant value, that has a DC value. And this is what is typically done, because in practice what happens is that the mechanical part behaves as a low-pass filter, and therefore filters out all the harmonics of the signal and only retains the DC term. Okay, so basically there is an effective filter which is done by the mechanical part in movement. Now you can also verify here graphically the fact that if we change the duty cycle, we can change the average value between a maximum value, which is V in, and the minimum value, which is minus V in. So we can apply both the positive and the negative value at the output, just by adjusting the duty cycle. And of course, in this case, the duty cycle really depends, since we are comparing a triangular wave function with a V control, the duty cycle exactly depends on the level of V control. So this is, let's say, an analog equivalent of what actually happens in a full bridge converter. Of course, if we, for example, call this quantity Vmax, the maximum of the triangular wave, what we have is that the duty cycle is equal to the duty cycle of B, which is probably easy to compute, is equal to 1/2 plus V control so let me write here dA. dA is equal to V half plus V control over V max, and dB is equal to 1/2 plus minus V control over V max. It's easiest for me to write those and then to show you that those are correct, okay, instead of the rhyme, because it's pretty intuitive. You can see that, for example, if V control is equal to 0, then the duty cycle has to be 1/2 for both A and B, right? And of course this is true. And on the other hand, if V control is equal to V max, then the duty cycle of A is always 1, because the condition here is always true. So if we move V control to V max, we increase the A and we decrease the B, which is what we have shown here. So these are the conditions, and therefore VA, which is equal to dA minus dB times V in, if I do the difference, is equal to V control over V max times V in. Therefore, if V control can go between V max and minus V max, this number can go between +1 and -1, which is what we want. Okay? Now, to complete the reasoning on this point, there are a couple of things that are important. Why I've shown you this plot? Because, or actually this is easy to draw, but in practice, in a typical full bridge converter, this comparison of V control of V max is not something that you do with analog signals. It's something that is done inside the microcontroller with a code. Basically, the triangular wave function is just a counter that goes up to a maximum value, then decreases and then goes up, so it behaves like a triangular wave, and V control is a reference number with which the number, the variable which represents the triangular wave function is compared. So all this part is done in practice in a microcontroller, and then what is important is that those conditions control some output pins which are connected to the gates of 4 different NMOS transistors that can be opened and closed. So all the logic is done in a microcontroller. The microcontroller must have 4 output pins, analog output pins. Each of those goes to the gate of 1 different transistors, which acts as our switch. This is just one possibility for for obtaining this voltage. Of course, there are also other possibilities. Maybe it's not that important because the principle does not change. The other thing that I want to mention is the fact that with this same principle, I can also obtain an inverter, because if I need to transform a DC power, a DC voltage, for example, into an AC voltage, as we usually do in a UPS. UPS means uninterruptible power supply. Of course, you have a battery inside the UPS, and then you have to provide a 220 volt alternate current for different types of equipment. And you can use exactly the same type of circuit, but instead of having this type of filtering, and instead of extracting only the DC voltage, in that case what you want to do is to have a rectangular wave with a duty cycle equal to 1/2, so almost a square wave. And then you just want a filter to only extract the first harmonics. Okay, and in this case, for example, from a DC voltage you can obtain a 50 Hertz AC voltage, which can be used to provide a power supply to an AC load. Okay, so the same type of basic circuit, a full bridge DC-DC converter, is typically also used for uninterruptible power supply. So it's a very basic circuit. Okay.